Login accepted.
So, hello everyone, my name is Grzegorz Piwowarek, and it's really weird to see all of you right here in person. It's been a long break for me and for all of you, but luckily we seem to be back to normal. But it's not the case for the CompletableFuture, because apparently there's quite a lot of interesting things which can be not considered normal. And this is the reason why I'm here with you today. CompletableFuture appeared long time in Java. Well, not Java 1.8, that was a long time ago. The early concepts of future appeared in Java 1.5, in Java util concurrent, but it wasn't suitable for a lot of stuff. And CompletableFuture is like is the main actual tool, one of the main tools that you would use for asynchronous programming in the core Java. Unfortunately, it has some quirks. There are some things that you might consider not normal, weird, or at least unexpected. And this is what this talk is about. I will show you pretty much 4 things about CompletableFuture that you probably didn't know about, but you should probably do. However, if you are not a beginner, if you are a beginner, if you've never worked with it before, there is still some stuff that you should be able to learn. So I am a lead architect at Hazelcast. I'm working directly in the CTO office, which means I'm responsible for, I'm not permanently tied to one product team, but I'm kind of overseeing a few of them. You can find me delivering workshops and blogging at my site, forcomprehension.com. I haven't been very good at persistence blogging recently, but I'm coming to return to that. So the topic for today is asynchronicity. And what's the difference between synchronous and asynchronous processes? If you have 2 processes, A and B, that are synchronous, it means that the process A starts, the process A ends, then the process B starts, the process B ends. As simple as it can be. But if we make them asynchronous, they are no longer tied to each other. Process B no longer needs to wait for the process A to start. And in most cases, well, the process B will just start just on its own, on some other thread, continue, and wouldn't really care about the process A. If it started, if it completed, the process B is just asynchronous. And it can be useful, because we don't always want to run everything sequentially. But it also poses some challenges. Because if you create that asynchronous process and run something on the side, now how do you actually return, how do you reach and get the value that was returned there? Because if let's say I want this computation to be done on the side, and well, for some reason, I want this value back, right? I didn't just run it just to end, and I care about it. I want the value to be back. And this is tricky. And this is what the concept of future promise is about. It's like a container with a value inside, which will spawn at some point in the future. So we have some asynchronous method, we run it, we get a future of integer. In a kind of similar way, we would get an optional of something. And we know that at some point in the future, in this container, our result will appear, or not, if there was an exception. And the good part about it is that between we actually reach for that actual value, we can do other stuff. So as you can see, we can, well, those are pretty much benefits of parallel computing. What's also quite important to add that every method can be asynchronous. It's not just those methods that return futures, but essentially we can create our own executor service. We can submit any method in there and receive a future containing the result of that method execution. And in Java, we've had 2 most important implementations, the standard Java util concurrent one from JDK 1.5 and CompletableFuture from 1.8. However, if you look at Java Future, it was kind of very limited regarding what it could do. Well, we can actually have a look at and see how it looked like. So if you have a look at the future, let's call it a future task, because that's actually one of the main implementations of the future in Java. If we try to call any method on that object, you see that there is just get, run, is cancelled. Actually, if we narrow the type to a future, we'll see even fewer methods. There's just get with timeout, get without the timeout. There's cancel, is cancelled, or is done. So as you can see, there is not much you can do with that. So the main problem is that it provides only blocking API. And the problem is that if you run something asynchronously and you want to wait for its execution, you probably don't want to. There are scenarios in which you want to block, but you should be able to do more than that. So usually it's a kind of unwanted behavior, what you saw in the past here. You don't want to just submit something asynchronously and then call .get and wait for that, because kind of it defeats the purpose of asynchronicity, because it will essentially perform. You could not involve third-party executor. You could just run it in the same method that called that .get method. There is a limited opportunity when it comes to exception handling. And to be fair, it's pretty ugly. So if you have a look at the .get method, it will force me to implement some, to handle some exceptions. That's an execution exception. That's an interrupted exception. As you can see, it's not very aesthetic and convenient. Another problem is that the future can't be manually completed. What does it mean? If you look at the future, that's just an interface. But essentially, in Java 1.5, there is this inherent one-to-one mapping between a thread that's executing a task and the future. So if you have a look inside the future task and the class, you'll see that it implements this weird interface, runnable future. And as you could expect, runnable future is both. It's a runnable and a future. It feels a bit weird. The approach in JDK 1.8 with CompletableFuture is slightly different, and we'll get to this in a second. And one most important part is that futures can be easily combined. So this is the great power of asynchronicity is that you can actually juggle and perform interesting computations of multiple processes being performed asynchronously. So imagine you are building some trading exchange platform. And you really care about low latency, or at least as fast response as you can get. And let's say you are using third-party currency service, which gives you the current currency rates. And this service is flaky, or sometimes responds in 10 seconds and not in half a second. So just in case, you might want to use 3 or 4 or whatever currency exchange providers. And at this time, you would issue, let's say, 4 or 5 parallel requests at the same time. And it would be convenient to wait only for the first one that arrives. If your API is like that you have only get and cancel methods, it's very complicated. Obviously, it's doable. So if you are scheduling your own operation on your own custom thread pool, you can, for example, create your custom queue, some concurrent queue, make sure that every value is not just directly returned, but pushed to the queue. Then you can block on that queue. And as you can see, this is where it gets pretty complicated. Doable, but complicated. And this is where, before JDK 8, Guava came into play and introduced listenable future. And it allowed you at least to provide listeners that would act on a value that was, when the value would arrive in the future, it would execute a listener. That was pretty convenient. a bit better. But as you can imagine, before JDK 8, when we didn't even have lambda expressions, that was pretty disgusting, because every function provided to a listener needed to be an anonymous inner function, and there was no way to provide your own lambda expression in such a concise form as we can do as we've been doing for the last 8 years. However, the approach to JDK 8's CompletableFuture is totally different. So let's get rid of all of that. Let's make it integer as well. And the biggest difference is that you can just complete it manually, which it doesn't sound very impressive, I can imagine, right? It's just putting a value into a container. But this means that there is no this inherent connection between a thread that's executing a future and the future itself. So this can be completed from the same thread or from any other number of threads, which allows quite interesting things to happen. And this is one of the actual reasons behind some of the issues you'll see in a second. And now, if you have a look at all the API of the CompletableFuture, as you can see, it's quite beefy. That's quite a lot of them. I would say there is way more than actually necessary. But that's another story for another time. And what it allowed is that now you can think declaratively about your asynchronous processes and how you combine them together. So if you, let's say, want to combine two of them together, you create two futures, you call then combine, you provide a method, and you don't need to worry about synchronizing them. If you want to do the same on the first value of the value that arrived first, it will look more or less the same. That's really convenient. There's a lot of value in that. But this talk is not about the CompletableFuture and the basics. If you want to learn the absolute basics, there is a great talk by Tomasz Norkiewicz about that. But in this talk, we'll be focusing only on those weird parts that you need to know about. And the first thing I'd like to talk about is the cancellation of the future itself. So let's go back to our example for a second. Let's go back to the old school future task. By the way, future task is not something that you would normally create by yourself. That's usually something that would be created for you when you are not looking. But it's probably one of the easiest things to create an implementation of the future. And now, look, if you want to cancel it, you can provide true, may interrupt if running, which means that internally, if you have a look at what's happening, let's hope we can dig deeper. Future task. Essentially, you will dig down and see that the thread executing the task behind that stuff will get interrupted. And as you can see, this is pretty convenient. We have a task running, we receive the handler to the value, which is the future, and we cancel it. Well, the thread receives an interrupt. If you've handled interruptions properly, then the thread will abort execution when it's possible. But that's not the case with CompletableFuture. So let's go back. Let's create a CompletableFuture of some. Let it be integer. Let's say that it's executing, and let's join and make it run, because that's also an option. We can join and make it run. Obviously, this will never complete because there are no jobs that would complete that. But we can already cancel it. And we can provide the same argument as in the past, may interrupt if running. But let's have a look inside. What's in there? Let's have a look at the documentation, at the thing that none of us looked in the past. So, when in the cancel method, you provide a Boolean flag, which pretty much instructs future if it should interrupt the underlying thread. And you can see here that this may interrupt if running flag They literally wrote it here. This value has no effect, because interrupts are not used to control processing. So if you cancel a CompletableFuture and later join on them, you will get an exception. And that's correct. It will look like it got canceled. So let's, for example, join now. There's an exception, cancellation exception. And the future itself is canceled. But the future is canceled, the object that's used for retrieving a value. The thread that's lying internally, it's not canceled. It's still running. Because guess what? There is no one-to-one mapping. With the old school future, we had this convenience, well, this nice side effect of this one-to-one mapping that we could cancel underlying threads. But if there is one future returned, and there are 5 threads competing for the same, to complete the same future, which one would you actually cancel if you try to figure which thread would you actually cancel? So imagine a scenario like this one. You have CompletableFuture 1, you call then apply, then combine, and then run, and each stage returns a new future. What happens if I cancel that one? Should I propagate the cancellation up to the producer? Or should I cancel only the last one? And if my future is potentially completed by n number of threads, do I interrupt all of them? And this is a non-trivial issue. And the way they decided to move forward is to pretty much don't do any cancellations. For example, in my library, I allowed myself to hack it this way because I knew that in my setup, I controlled both sides of I controlled both the producer of the CompletableFuture and the consumer. I allowed myself to hack it by introducing actually a future task internally. But this is not an option if you are just receiving CompletableFuture by yourself. So a note for you, remember that cancellations don't work. So probably if you are relying on that, so you probably have some threads running in the background longer than you would expect them to. Another thing that I'd like to bring your attention to is there are 2 very handy methods: CompletableFuture AllOf and AnyOf. And as you can see, they sound pretty, what could they be doing wrong? It sounds, let's have a look, CompletableFuture, AllOf, and it accepts a list of futures. So let's go for 2 futures. Let's make it integer. Let's make the second one. I provide 2 futures, and it seems to compile. And how does it work? Well, when I see this, AllOf, I provide a list of futures, and I return, and I get a combined future. I think that this is that's the combined future that returns all the results of when all those single futures completed, it returns a combined result of all of them. Sounds good. But you've probably, if you've been paying attention, you've started noticing something weird that's happening here. Starting with that void here. Wait. So you are telling me that there are those 2 futures that I'm waiting for their results. And in the combined future that waits for both of them, we get a void and not the results of those futures. What's going on? So let's have a look at the actual signature, and you might see a bit more weird things. For example, that var args over there, it doesn't really utilize generics. Utilizes generics, but with the question mark, not very useful. Which means that if I go back here, I create an integer, and I create another future, let's say of type string. This still compiles. If this is integer and this is a type car, it will work as well. And it's really weird, because why would I ever wait for, let's say, a couple of futures where the first one returns a string, second one returns a car, third one returns a person? that sounds like a weird use case to me, because in most cases we'll be waiting for futures of the same type, or at least from the same hierarchy of types. No, well, the object doesn't count. And what's more, its behavior is might be a bit unexpected. So let's do something like that. We have an integer and a string. CF1 will complete with integer 1. CF2 will complete with empty string. And if we call AllOf and join, wait for the result, it completes immediately. Well, that's to be expected, because both of those futures are completed. But what if instead of completing one of them, we throw an exception? Complete exceptionally, let's say with null pointer exception. How would you expect this to work? What if there's an exception thrown? Well, probably. The whole operation didn't complete successfully because at more than 0 sub-futures actually failed, which means that the whole future, well, should be failed as well. Let's run it. And that's correct. The exception was actually propagated directly to this future. But as you can probably guess, there is something interesting over here. So the issue is, imagine that this completion comes very late in the process. So let me create quickly future run async. I'll provide a line here. And let's add some waiting. Let's say 5 seconds. Oh, please forgive me for this interrupted exception handling. Those are just exercises. And let me complete the first one after some time, after 5 seconds. So I'm running it. And we already know that the second failed already, right, immediately. But we still did need to wait 5 seconds for this to return the actual, for this to propagate the exception. The reason it's like that, because AllOf waits for the completion of all of them. It doesn't short-circuit an exception. So if you have 100 futures, and let's say all of them are executing for 1 minute, and there is one future that fails in the first second, it will still wait all the time for all the futures to complete. And in this, if you think about it, it makes that void that's inside makes a bit of sense, because the AllOf is supposed to be used as a signaler. If all of those futures completed, regardless of its status, then complete. But this is not what we often need. Okay, in applications we care about a bit different semantics. And for example, that's a piece of code from one of the popular open source frameworks. There's quite a lot of magic here, quite a lot of smart stuff. But at the very end, they just call CompletableFuture AllOf and of futures, which means it has the same problems as what I just showed you. And the problem is, and that's definitely not the behavior they wanted. Oh, I showed you some spoilers, so I won't be coding that by myself. So there is actually a way to fix that, and to fix it by yourself. I'll show you how to do this. However, in most cases, whenever you need this kind of semantics, like real AllOf semantics, you can most likely find this piece of code somewhere all over the web. So the first thing that we would need to, in order to fix it, is to actually change the signature. The signature here is totally broken, because what we don't want to accept features of any types. We want to accept features of the same type. So this is what this T, generic T, gives us. It guarantees that the list of features that we accept has always the same type. But what's more, if you are waiting for all of the features to complete, why not just wait and hand over those results on a silver platter? We've waited for all of them. They are there. Let's give them right away. That's why we are returning list of t, list of all the t's that came from those futures. And now there are two things we need to remember about. First thing is a pretty tricky one. You just need to, we can actually use AllOf. It's pretty useful because its internal implementation of the internal propagation of the signal is pretty sophisticated and pretty useful. So I don't want to get rid of that because it's pretty useful. So we can reuse the AllOf. We can convert that list to an array. By the way, remember to always, if you are converting collections to list to an array, remember to always put a 0 here. And the explanation is given here by Shipylef. It's 60 pages of assembly code that you can read and understand why it's important to go for a 0. And once we already know that this AllOf has completed, we can totally disregard that void part from then apply and just read back to all the futures right here because we know they're already completed and we can extract all the values from there. There's just one problem. The AllOf doesn't short circuit on exception, but in most cases we would like to. So we need to do it by ourselves. In this case, we are introducing a very simple race. So we iterate over all the futures, and we say whenever one of them completes and completes with an exception, just complete that our future with an exception. And that's how we got our AllOf that accepts futures of the same type, returns a completable future with the list of results, and short circuits on exception. Another funny part, and a bit unexpected, can be with the AnyOf method. However, you probably might have an idea what's wrong with this one after hearing about what I told you about AllOf. So let's get back here for a second. Let's go here. We have the same setup as in the past, as earlier. We go in the future, AnyOf, CF1, CF2. So as you can see, AnyOf, essentially. When I accept a list of futures, and I want to say, give me any of those whenever they complete, in most cases, I would like to have the same, will be operating on futures of the same, holding same types. But in the case, again, we have a question mark, which means we can pipe any future we want. And it returns, well, you would expect that it returns completable future with a void, like with AllOf, right? But no. It returns completable future with an object inside, which feels inconsistent, because if they decided to do something non-intuitive in the AllOf method, why, well, stick to the same philosophy while we got doing AnyOf. But in this case, they are returning an object, which you can cast to the type you are expecting. And as you can imagine, it's not very convenient. But that's not that bad. You can work it around. But what do we do? What to do? How does it behave? So instead of doing that, let's just join and see. So whenever there is a list of futures, and when I think AnyOf, I'll try to think I want to wait for the first successful future to complete, right? And in our setup, the successful completion comes after 5 seconds. What happens immediately is the completion with a null pointer exception. And look what happened. Immediately, the future completes with an exception, null pointer exception. So as you can see, it's funny, because it actually returns any future that completed first, regarding if it was a successful or an exceptional completion, which again might be not what you were looking for. Because in most cases, you would be looking for something that gives you first that actually worked and gave you the right result. And again, I spoiled the answer a bit by going too far in my slides, so let's just talk about this here. That's something that you can work around, again, by yourself. You can fix the method signature, you can add more methods. I mean, you can create your own completable future, empty instance, complete it manually whenever any of those completes, and then introduce arrays. So whenever there is an exception, Whenever all of them complete exceptionally, then eventually complete your original one. Again, probably not something that you need to think about. You will find it easily online. But I would like you to be aware that such a problem or deficiency of that particular method exists. So we are done with those two methods and cancellations. And here we arrived at one of the most interesting problems, not problems, like interesting aspects of CompletableFuture. And that would be completable futures versus threads and the thread management. In JDK 1.5, with old future, it was very easy. You would, just like you told you already, you'd create an executor service, you submit something there, you receive a future, you cancel it, you know that it's executed on a method that's coming directly from that executor. Let's actually see that. So let's get rid of that. Let's create a simple executor service. We submit some task that will return the thread name, print out the thread name. Let's say and return, let's say 42. There is that future, and we can wait on that. Obviously, I'm not going to handle those exceptions. And you can see that the name is pool1 thread 1. If you don't trust me that this is this one, we could quickly create a new thread factory over there that returns new thread with the name Devoxx and R. Obviously, make it a lambda. So now you have a proof that it executes on that particular thread pool. I will roll it back because we will need actually the IDs next to the thread names, and it works. That's very easy. But it gets a bit more complex with CompletableFuture. Because now, imagine if you have this one-to-one mapping, again, it's easy, because there's something that starts, completes, and ends, the thread dies, or gets reassigned, whatever. But now, when you obtain a CompletableFuture instance, you have no clue if there is something executing it. How many threads are there? From which thread pool? And there is the case where there might be actually any. There might be 0 threads executing it. But what's more, let's say you are combining those futures, you are calling those declarative methods in it, like run async, then run, then run. And now it's not really obvious because, well, if you receive a future with from some method, you would expect that some thread is executing, will complete it. That makes sense. But what if we run those methods, like run async, after that thread already finished doing its processing? So what other thread should pick it up? It's not an easy answer. So let's keep that executor for a while. It will be unused for a second. The future, we go submit async. Let's say it returns 42. As you can see, this is a CompletableFuture, separate one, so that you believe me. And then let's say let's add one log line here. Thread current thread get name, print it out, return 42. Let's add maybe a bit of, oh no, without waiting. Let's add something here. Let's make it then run and print out the thread name again. Now we can join, make it run. Not printf, but I want that print line. So look what happened here. Something really peculiar. So first things first, I didn't really need to supply any thread pool to that particular example. I just called supply async, and for some reason, it executed somewhere. It executed on a ForkJoinPool. What is it, and what we need to be aware of? We'll get to this in a second. But look what happened with the second one. Then run, we printed out, and it printed out the main thread, which is the main, well, as you can guess, is the thread executing that method. So imagine you're receiving a future, you are calling a method, you are thinking it's being executed asynchronously. But if there is a main thread, it means that we are essentially blocking the main thread on something that returns a future. And it's a bit unexpected, don't you think so? It's a bit weird, because if I'm blocking here, let's say for 10 seconds, again, forgive me that interrupted exception handling, it turns out that we are effectively blocking the main thread for 10 seconds on something that returns the future. That's terrible. In this case, it worked, because actually we were in this happy scenario where this method was already, that call was already registered before that finished. But if we run it a few times, you will see again the same scenario, that the main thread will appear right here. And as you can see, so this is non-deterministic. You don't know when, oh, you can see there's a main thread again. We don't really know when it will be executed on the main thread versus on the thread coming from a thread pool. So yes, this is a problem. However, something that you need to remember about is that there is a reason why there are so many methods in the CompletableFuture API. So if you have a look at then run, if you apply your code completion here, you will see there are multiple other methods. Then run async, for example, which forces the execution of that step on a particular thread pool. So we go then run async. Where is that? It's here. We provide the executor over here. The same we can do with the supply async, which means we are enforcing one particular thread pool to be used. And now we have those guarantees. This will be always run asynchronously on that pool of my choice. So it doesn't matter how much I'm waiting here, and if that completed fast or is immediately or later on, it will always run on the same thread. By the way, this is not stopping because that pool has non-daemon threads inside, which means it would need to be shut down in order for the JVM to stop. So the first very important lesson is that always use then run async methods for non-trivial Lambda expressions. Because if you go for then run here, or then apply, and it's an integer, and you do something like that, that's not an issue. If it's going, if it will be run in the main thread, it's not an issue at all, right? But if you are planning to make blocking calls and block for longer, then always remember to use then run async and provide your own custom executor over in there. So as you can see, this can get pretty interesting. But at the beginning, when I showed you the first example, you actually could see that I didn't actually provide any thread pool. I just went for supply async, and it worked. And it all was executed in a common ForkJoinPool. And this can be problematic, because that's not normally a thread pool you would use as a default. The way the ForkJoinPool works is that it's a thread pool that's static, that's in the center of your JVM, and it's used for stuff like fork-join tasks, for parallel streams. It's used also as a default for CompletableFuture, and it will be used as a source of carrier threads for virtual threads from Project Loom. ForkJoinPool is a pretty interesting one. It's designed to maximize throughput for CPU-intensive tasks. And if it's designed for that, this is also the reason why the parallelism of the ForkJoinPool is strictly correlated with the number of cores you have on your system. Well, not really on your machine. Well, not really a course, but what one method returns. So if you go over to this method runtime, there is this available processors method that returns the number of cores you have on your machine. It can lie sometimes, because processors with hyperthreading will pretty much lie to you about how many physical cores you have. But you need to be aware that this is the source, this determines how many threads are in the central thread pool. And let's assume your system is running something CPU intensive on that pool. Normally, you don't want to have more threads, because if your CPUs are running at full speed, if you add more threads, it won't get faster. At the end of the day, the CPUs it's something that's executing those tasks. But if you're adding more threads and more parallelism, more than you have CPUs, that means you will waste more time on doing bureaucracy between thread switching. And now imagine, you go by default to your CompletableFuture or parallel streams, and you submit a lot of blocking tasks that land on that ForkJoinPool. And suddenly, this pool, those threads are busy doing nothing, while CPU-intensive tasks are waiting in the queue for their turn. So this can be really bad. So the rule of thumb is to always remember about providing your own executor service, whatever you are doing with CompletableFutures. With parallel streams, you can't do that. I wrote a library that solves that problem, though. But with CompletableFutures, you don't have any option. I mean, you have an option to provide your own executor, which is not a default. If I remove that executor from here, it will still compile. So remember about that. What's also funny, look, the deadline async method actually is overloaded. There's an option that doesn't accept any executor. So if I remove that executor from here, guess what? It will run on a ForkJoinPool again. So this can be pretty tricky. But that's not all what is quite surprising in here. Because if you look inside run async, normally if you have a computer with multiple threads, the common pool parallelism will be more than one. And you might be thinking, but there is a very specific case. Look, there's this if use common pool, if this is one, it doesn't use ForkJoinPool common pool. It uses thread per task executor. Thread per task executor. And it's a very simple implementation of a thread pool, of an executor. It just creates a new thread and spawns it. So it's not really a pool, right? It just creates threads. And I understand why it's like that, because if you had just one thread in a pool, it would be very easy to end up with deadlocks. So it's better to be more wasteful and create threads than to end up with a deadlock. And you might be thinking, Grzegorz, but I don't know how about you, but it's been a long time since I had only one CPU on my computer. It's probably way more than that. But guess what? We are in the world of containers, Kubernetes, cloud. It's quite possible that some of your workloads might be running on the one CPU without you realizing that. Obviously, that's not physically to be one CPU. It would be a logical restriction to one CPU. But this actually happens. And if the runtime getRuntime available processors returns 1, it means that suddenly, if you relied on defaults, it will all run on this, well, pretty much the thread executor that just creates random threads out of nowhere. That I showed you already. I showed you already. Those are just my backups. And the last thing I'd like to show you today is an interesting case of apply to either versus exceptions. If you've been paying attention, you probably know where I'm going, what I'm trying to show you right now. But there is something very weird about how apply to either behaves. Actually, let's go for one final piece of code. So we have that CompletableFuture, CF1. Let's make it an integer. There's CF2. And let's do something like that. CF2 apply to either, CF2, do nothing, and let's just join and get a value. So let's actually print it out. And let's complete CF with 1 and CF2 with 2. You run it, and we expect to want to have one of those printed out. And that's to be expected, right? Because we are trying to apply to either CF1 or CF2. Right, we got 1 at that time. We could have gotten 2, it doesn't matter. So, but let's say this never happened. So we are completing only the first one and never complete the second one. Guess what? We got 1, right? As expected. Nothing weird here. Let's try the other way around. Let's try complete only 2 and not 1. Works. Totally as expected. Boring, right? So let's try to add exceptions here. And again, completed with 1. So we have 2 futures, CompletableFuture 1 and 2. First one completed with the value of 1. Second completed with null pointer exception. Nothing fancy here. That's how we would expect it to work, apply to either. What if we switch them? What if we switch places? What if CompletableFuture 2 is completed with the value of 2? Maybe to not make it very confusing. And CF1 is completed with null pointer exception. And here you go. Here you have your completion exception, null pointer exception. We have 2 futures. At this point of executing this method, we have 2 futures. One is completed with a success. One is completed with a null pointer exception. It knows already that there is a valid value in there, but it still decides to throw an exception because this is what happened here in the first one. So this is probably quite surprising and quite bad. And again, the solution to that is to pretty much to rewrite it by yourself. And it seems like we've arrived at the end of this presentation. So as you can see, those were just 4 things, but I think pretty major. So what you need to remember about is that CompletableFuture can't be cancelled. Well, it can be, but the cancellation won't be propagated to the underlying thread. You need to remember that AllOf and AnyOf methods, they treat exceptions equally to the values, to the actual values. So don't be surprised if AnyOf throws you an exception first, although there is a second value that's actually not exceptional. Third thing is the threads. So by default, CompletableFuture uses ForkJoinPool that you probably, in most cases, you want to avoid. There are valid scenarios for that, but if you want to use that, you need to know what you are doing. And this is not a very reasonable default. So just remember about providing executors everywhere in the CompletableFuture, unless you are doing something trivial like basic string operations, integer incrementations, or anything that doesn't consume significant time, especially on blocking. And lastly, remember that in many cases, CompletableFuture treats exceptions in a special way, which can result in such problems like you've just seen with apply to either. So that was all for today. There is some time for questions. If you want to find slides for this presentation, you need to scan this QR code. You can find me on Twitter. And thank you very much.